Dear students, after studying this module, you shall be able to understand the position, intensity and shape of an absorption band, understand the effect of bond strength on absorption frequency, understand how hydrogen bonding affects the absorption bands, and also know about the possible modes of vibration in aliphatic and aromatic hydrocarbons and their frequency values. Let us now come to the study of position of an IR absorption band in the IR spectrum. The amount of energy required to stretch a bond depends on the strength of the bond and the masses of the bonded atoms. Now, the stronger a bond is, the greater energy is required to stretch that particular bond. The frequency of the vibration is inversely proportional to the mass of the atoms. So, heavier the atoms, the vibration frequencies will be lower. The approximate vibration frequency of a bond can be calculated from the equation derived from the Hooke's law, which states that nu bar, that is the wave number, is equal to 1 divided by 2 pi c square root of k upon mu, where mu is the reduced mass and mu is equal to m1 multiplied by m2 divided by m1 plus m2. Now, m1 and m2 are the masses of the two atoms involved in bonding, and that bond is to be stretched. C is the velocity of light, and as you know, its value is equal to 2.998 into 10 raised to the power 10 centimeter inverse. K is the force constant of the bond. Now students, for a single bond, single CC bond, that is, it is approximately equal to 5 into 10 raised to power 5 gram per second square, and it doubles and triples for every double CC bond and a triple CC bond respectively. The force constant is a measure of the strength of the bond. Thus, the value of stretching frequency of a bond increases with increasing the bond strength and decreasing the reduced mass of the bonded atoms. Now students, the triple bonds, as you know, are stronger than the double bonds, followed by the single bonds between the same two atoms involved, and hence vibrational frequency is of the order of triple greater than double greater than single bond. As you can see, the values for triple, double and single bonds are given here, and you can see how the force constant is increasing for triple bond, then double bond, then single bond. As the atom attached to carbon, a particular atom, say carbon, increases in mass, the reduced mass increases, and hence the frequency of vibration decreases because they are inversely proportional. Now consider the bond attachments to carbon. One is hydrogen, other case it's carbon, the third case is oxygen, and the fourth case is chlorine. Now you can see that for CH bond, the wave number becomes, or the energy becomes 3000 centimeter inverse, then 1200 centimeter inverse. For carbon and oxygen linkage, it is 1100 centimeter inverse, and for carbon and chlorine, it is 750 centimeter inverse. So with increasing mass, the wave number decreases because they are inversely proportional to each other according to the Hooke's law, as I have already told you. Now we come on to the intensity of absorption bands. The intensity of an absorption band depends on the change in dipole moment of the bond associated with the vibration. The greater the change in dipole moment, the more intense is the absorption. The dipole moment of a bond is equal to the magnitude of charge on one of the bonded atoms multiplied by the distance between the two charges. If we have two different atoms, there will be an electronegativity difference, and larger is this electronegativity difference, the more intense the absorption band will be. The stretching vibration of a OH bond will be associated with a greater change in the dipole moment than that of an NH bond, because OH bond is more polar because oxygen is more electronegative than nitrogen. Now consequently, the stretching vibration of the OH bond will be more intense. Likewise, the stretching vibration of a NH bond is more intense than that of CH bond because NH bond is more polar, because N is more electronegative than carbon. Now you can see the increasing polarity order over here, being OH being the most polar, then NH, then the CH bond. And with the increasing polarity, the intensity is also increased. Now the intensity of an absorption band also depends on the number of bonds responsible for the absorption. For example, if you compare the IR spectra of methane to that of octane, the octane molecule will have a much more intense CH peak because it has many more CH bonds than methane, because methane has only 4 CH bonds and octane has much more. The concentration of a sample used to obtain an IR spectrum also affects the intensity of absorption bands. Concentrated samples have greater number of absorbing molecules and therefore more intense absorption bands are observed in case of more concentrated samples. Let us now consider the shape of absorption bands which are obtained in IR spectroscopy. The shape of an absorption band can be helpful in identifying the compound responsible for an IR spectrum. Now let us take an example of both OH and NH bonds which stretch at wave numbers 3100 cm inverse, but their shapes are very distinct and thus it is the shape of the band which is responsible for the distinction of the two bonds. An NH absorption band which comes at around 3300 cm inverse is comparatively narrower and less intense than OH absorption band in alcohol, and the OH absorption band of an carboxylic acid comes around 3300 to 2500 cm inverse and it is broader than the OH absorption band of an alcohol. Now you can appreciate by studying the shape of the band one can easily find out the nature of linkage involved in that bond, even if they fall at the same frequency values or the wave number values. Now students, let us now consider the factors influencing the vibrational frequencies. The value of vibrational frequency of a bond calculated by Hooke's law is not always equal to the observed value, because Hooke's law comes under ideal conditions. The force constant is changed with the electronic and steric effects caused by other groups present in the surroundings. Following are some important factors that we are going to discuss in this module which affect the vibrational frequency of a bond. Now first we will consider the effect of bond order. Bond order affects the position of absorption bands. Higher the bond order, larger is the band frequency. A CC triple bond is stronger than a CC double bond. So a CC triple bond has a higher stretching frequency than a CC double bond. The CC bonds show stretching vibrations in the region of 1200 to 800 cm inverse, but these vibrations are weak and of little value in identifying the compounds. Similarly, a carbonyl C double bond O bond stretches at a frequency, then does a CO single bond, then a CN triple bond stretches at higher frequency than a C double bond N, which in turn stretches at a higher frequency than C single bond N. Now let us come on to the second effect which affect the absorption frequencies, that is resonance and inductive electronic effects. Whenever we discuss about the IR band, students, a range of frequency for each stretch is usually assigned, as the exact position of the absorption band depends on other structural features of the molecule. These can be electron delocalization, the electronic effect of neighboring substituents, and hydrogen bonding. Important details about the structure of a compound can be revealed by the exact position of the absorption band. For example, the IR bands for the carbonyl group in 2-pentanone and 2-cyclohexanone appears at different frequencies. The 2-cyclohexanone absorbs at a lower frequency because the carbonyl group has a less double bond character due to electron delocalization. Now, if you put an atom other than hydrogen, that is aldehyde or carbon, ketone, next to the carbonyl group, it also causes shifting of the position of the carbonyl absorption bands. Whether it shifts to a lower or to a higher frequency, that depends on the electronic effect, that is the inductive and mesomeric effect of the atom. Different substituents on carbon of the carbonyl changes the electronegativity of the carbonyl group due to inductive effect arising due to the different electronegativities of the substituents of the carbonyl carbon in compounds of the type RCOZ. Now, it also involves the electrons in the sigma bonds. The mesomeric effect involves the electrons in the pi and non-bonding orbitals, and it operates in general opposite to the inductive effect. These effects cannot be isolated from one another and at a time only one of them can be applied to determine the approximate results. Now, you can see here the figure shows both resonance electron donation and inductive electron donation. Electron releasing groups attached to the carbonyl group tend to favor the polar contribution by mesomeric effect and thus lower the bond order of the carbonyl bond, that is due to the less double bond character, and hence resulting in a decrease in carbonyl stretching frequency. Now, electron withdrawing groups suppress the polar contribution with an effective increase in the double bond character and hence resulting in the increase of frequency of absorption. The predominant effect of the nitrogen of an amide is electron donation by resonance. Therefore, the carbonyl group of an amide has less double bond character than the carbonyl group of a ketone, and hence amide has low CO bond IR frequency than the ketone. Now, in contrast, students, the predominant effect of the oxygen of an ester is inductive electron withdrawal. Therefore, the carbonyl group of an ester has more double bond character than the carbonyl group of a ketone. So, the former appears at a larger frequency value. Now, you can see the values of each functional group. It is mentioned over here with the functional group colored in different colors. Now, if we talk about the CO stretching frequency, it appears in the range of 1250 to 1050 centimeter inverse. Now, if the CO bond is in an alcohol or in an ether, the stretching frequency will be towards the lower end of the range. If this CO bond is a part of carboxylic group, the stretching frequency will occur at a higher end of the range. Now, you can make out according to the functional group, the stretching frequency also changes. The position of the absorption varies because the bond in an alcohol is a purely single bond, whereas the bond in a carboxylic acid has a partial double bond character, that is due to the resonance electron donation by the OH group in acids. Now, coming down to esters. Esters show stretches at both ends of the range because esters have two single bonds, one that is pure single bond and the other which has a partial double bond character. So, it will come at both ends of this range as mentioned. Now, you can see one is an ester and one is a amide. You can see at the benzamide the stretching of carbonyl occurs at 1693, and in case of phenyl acetate the same stretching comes at 1730 centimeter inverse. Let us take this example in detail. In a specific example of benzamide and phenyl acetate, as the nitrogen atom is less electronegative than the oxygen atom in amide and is more labile and participates to a greater extent in conjugation, the presence of a greater degree of conjugation, thus the CO absorption frequency is relatively less than in esters in this case. In most of the cases, mesomeric effect works along with inductive effect and cannot be ignored at all. It is important to note that only inductive effect is considered when the compound is meta-substituted. Students, in case of para-substitution, both inductive and mesomeric effects become important and domination of one over the other will decide the wave number of absorption. This is clearly shown in the figure with 4 examples of para-substitution, but with different atoms, different heteroatoms, and you can see the values. Due to low electronegativity of nitrogen atom, the lone pair of electron participates more in conjugation in compound 1, as you can see, as compared to that in compound 3, as you can see in this figure clearly. Thus, in compound 1, CO stretching frequency absorption occurs at lower value compared to that in compound number 3. Now, in compounds 2 and 4, inductive effect dominates over mesomeric effect, and hence absorption takes place at comparatively higher frequency values. Now, coming to the last, that is the ortho substitution. In ortho substitution, inductive effect, mesomeric effect along with steric effect, the third factor, is also to be considered. In ortho substituted compounds, the lone pair of electrons on the 2 atoms influence each other through spatial interactions and change the vibrational frequencies of both the groups. Now, this effect is called the field effect. Now, let us come to the third effect influencing the absorption frequencies. The third in line is the hydrogen bonding. Now, students, the presence of hydrogen bonding changes the position and shape of an absorption band drastically. Frequencies of both stretching as well as bending vibrations are changed because of hydrogen bonding. The XH stretching bands move to lower frequencies, usually with increased intensity and band widening. The XH bending vibration usually shifts to higher frequencies. Stronger the hydrogen bonding, greater is the absorption shift from the normal values. The 2 types of hydrogen bonding, that is intramolecular and intermolecular hydrogen bonding, can be differentiated clearly by the use of infrared spectroscopy. Intermolecular hydrogen bonding involves association of 2 or more molecules of the same or different type of compounds, and it may result in dimer molecules as in carboxylic acids. Now, intramolecular hydrogen bonds are formed when the proton donor and the acceptor are present in a single molecule under special conditions that allow the required overlap of orbitals. For example, the formation of a 5 or 6 membered rings are typical examples of intramolecular hydrogen bonding. Now, the extent of intermolecular hydrogen bonding depends on the concentration of the solution, and hence the position and the shape of an absorption band also depends on the concentration of the solution. The more concentrated the solution is, the more likely it is for the OH containing molecules to form intermolecular hydrogen bonds. It is easier to stretch an OH bond if it is hydrogen bonded, because the hydrogen is attracted to the oxygen of the neighboring molecule. Therefore, the OH stretching of a concentrated, that is hydrogen bonded solution of an alcohol occurs at 3550 centimeter inverse, that is 3550 centimeter inverse. Whereas the OH stretching band of a dilute solution, that is with no or limited hydrogen bonding, appears at 3650 centimeter inverse. Additionally, students, hydrogen bonded OH groups also have broader absorption bands, whereas the absorption bands of non-hydrogen bonded OH groups are relatively sharper. Now, as you can see in concentrated solution, we have the band which varies between 3550 to 3200 centimeter inverse, whereas in dilute or with solutions with limited hydrogen bonding, the absorption band appears at 3650 to 3590 centimeter inverse. Now, hydrogen bonding interactions can also occur between functional group of solvent and solute. 3 classes of solvents exist which may lead to trouble when used for hydrogen bonding studies. First, compounds which contain hydrogen donor groups. For example, halogenated compounds which contain a sufficient number of halogens to activate the hydrogens present, such as chloroform. Secondly, compounds which contain non-bonded electron pairs such as ethers, aldehydes and tertiary amines. In addition, there are compounds which contain both types of group, for example, water and alcohols. There are only a few solvents that do not have the above characteristics, such as carbon tetrachloride and carbon disulfide. These still contain lone pair of electrons, but being on sulfur and chlorine are less available, and any interactions will be extremely weak with these atoms. Apart from the concentration and solvent effects, temperature also plays a large effect on the degree of hydrogen bonding in a particular compound. High temperature increases the extent of hydrogen bonding. Now, next effect which we are going to study today is the Fermi resonance. Fermi resonance is a phenomena which was first explained by the Italian physicist Enrico Fermi to account for shifting of the energies and intensities of absorption band in an IR spectroscopy. Now, sometimes it happens that two different vibrational levels have nearly the same energy. If such vibrations belong to the same species of molecules, then a mutual perturbation of energy may occur, which results in the shift of one towards the lower frequency sides and the other towards the higher frequency side. It is also accompanied by a substantial increase in the intensity of the respective bands. Now, Fermi resonance was first discovered in carbon dioxide by Enrico Fermi himself, and it is also found in the vibrational spectra of aldehydes, where the CH bond in the CHO group interacts with the second harmonic level derived from the fundamental frequency of the deformation vibration of the CHO group, that is 2 times 1400 centimeter inverse, that is 2 times the same band. This results is in a Fermi doublet which branches around 2830 centimeter inverse and 2730 centimeter inverse. Now, it is important for Fermi resonance that the vibrations connected with the two interacting levels be localized in the same part of the molecules. Now, next effect is the bond angles, which affect the absorption frequencies. Smaller ring requires the use of more p character to make the internal CC bonds for the requisite small angles. This gives more S character to the CO sigma bond, which causes the strengthening and stiffening of exocyclic double bond. The force constant K is then increased and absorption frequency thus increases. Characteristic absorption bands for hydrocarbons. These compounds have carbon and hydrogens only and may be saturated, unsaturated, aliphatics, cyclics and aromatics. The characteristic vibrational modes of aliphatic and aromatic hydrocarbons and their absorption frequencies are described in subsequent sections. Now, let us first take up aliphatic hydrocarbons. The stretching and bending vibrations of alkanes, alkenes, alkynes are described in the table. Now, as you can see, these values which are given for the symmetric, asymmetric stretching, wagging and twisting for various absorption bands in aliphatic hydrocarbons. Now, coming down to alkanes. Now, in alkanes, only two types of bonds are present, that is the CH and the CC bonds. The most useful bands in alkanes are those arising from CH stretching and CH bending. A methyl group usually shows two strong and distinct bands, one at 2960 centimeter inverse due to asymmetric stretching and the other at 2870 centimeter inverse due to symmetric stretching, while the methylene group shows asymmetric stretching at 2930 centimeter inverse and symmetric stretching at 2850 centimeter inverse. The CH bonds do not participate in hydrogen bonding and hence the frequencies are not affected by their surrounding chemical environment. The presence of several methyl groups in a molecule results in strong absorptions at these positions. The CH in-plane bending vibrations of a methyl group gives two bands, that is a symmetrical band at 1380 centimeter inverse and an asymmetrical band at 1460 centimeter inverse. Now the methylene groups give rise to four bending vibrations. First is the scissoring at 1465 centimeter inverse, the rocking at 720 centimeter inverse, the wagging at 1305 centimeter inverse and twisting at 1300 centimeter inverse. Now notice that the band at 1460 centimeter inverse indicates the CH asymmetric bending of both methyl and methylene groups, whereas the band at 1380 centimeter inverse represents symmetric bending of the methyl group only. Thus, the peak at 1380 centimeter inverse is extremely useful in detecting the presence of methyl group because this band is hardly overlapped to the absorptions due to the methylene and methane absorption bands. Now, students, the presence of two or more methyl groups attached to the same carbon results in the splitting of the CH symmetric bending vibrations. Now, for example, taking this compound known as isopropyl group in various compounds which give rise to two bands at 1397 centimeter inverse and 1370 centimeter inverse, and in tertiary butyl group which exists in many compounds, the two bands appear at 1385 centimeter inverse and 1370 centimeter inverse. This is clearly shown in the figure. Now the methine CH shows CH stretching and bending vibrations at 2890 centimeter inverse and 1340 centimeter inverse respectively, and are very weak with no practical significance. This is again, you can see all these values in the figure, and here is the IR spectrum of decane, this figure. Now coming on to cycloalkanes. Students, in case of unstrained cycloalkanes, the CH stretching frequencies are the same, that is between the range of 2800 to 3000 centimeter inverse, as in the case of acyclic compounds. However, methylene scissoring bands shift slightly to smaller wave number, that is 1417 hexane and 1448 centimeter inverse in cyclohexane. In sterically strained cyclic compounds, the CH stretching normally occurs at slightly higher frequencies. For example, the ring CH2 and CH groups in a monoalkyl cyclopropane ring absorbs in the range of 3100 to 2990 centimeter inverse, which shows the IR spectrum of cyclohexane. Now coming down to the methylene CH in plane bending vibrations. In cyclic alkanes, these shift slightly to smaller frequency as compared to their acyclic counterparts. For example, cyclohexane absorbs at 1452 centimeter inverse, whereas N-hexane absorbs at 1468 centimeter inverse. The CC bond vibrations appear as weak bands in 1200 to 800 centimeter inverse region and are seldom used for structural study. Now, whereas if you see, the CC bending absorptions occur at less than 500 centimeter inverse and are usually below the range of the IR instrument. Now next we come, students, to alkenes, which are doubly bonded. There are four major peaks associated with alkene molecular framework. These are out of the plane and in plane double bond C H bending, the C double bond C stretching and double bond CH stretching. Now in completely symmetrical alkenes such as ethylene, tetrachloroethylene, etc., C double bond C stretching band is completely absent due to the lack of change of dipole moment in completely symmetrical molecules. On the other hand, non-symmetrically substituted double bonds exhibit strong absorption bands. Now, olefinic CH stretching occurs at 3100 to 3000 centimeter inverse. C double bond C stretching occurs at nearly 1680 to 1600 centimeter inverse. The C double bond C absorption bands are more intense for cis isomers than the trans isomers because of symmetry in trans as compared to cis. Also, terminal olefins show strong C double bond C double bond stretching vibrations than internal double bonds. Now, conjugation moves C double bond C stretching bands towards lower frequency with increased intensity than in comparison to non-conjugated ones. In case of olefins conjugated with an aromatic ring, the C double bond C stretching appears at 1625 centimeter inverse, which is a strong peak, and an additional band at around 1600 centimeter inverse is observed due to an aromatic double bond. This can be clearly shown in the IR spectrum of cis 2-pentene here in the figure, as well as the trans 2-pentene figure also is shown, as you can see clearly. The double bond CH in plane bending vibrations near 1400 centimeter inverse, whereas double bond CH out of plane bending occurs at nearly 1000 to 680 centimeter inverse. These are shown in both the figures of trans and cis 2-pentene, as you can see. In compounds containing both olefinic and alkyl CH bonds, the bands above 3000 centimeter inverse are generally attributed to aromatic or aliphatic CH stretching, whereas between 3000 to 2840 centimeter inverse are generally assigned to the alkyl CH stretching. Now we come on to cycloalkenes. The absorption frequency of a double bond in an acyclic ring is very sensitive to the ring size, as has been explained above in the factors affecting the absorption frequencies. The absorption frequency decreases as the internal double bond decreases, and it becomes lowest in cyclobutene with an angle of 90 degrees. But after that the frequency increases again for cyclopropene. Now you can see the frequencies are given with their values as the ring size decreases from cyclohexene, cyclopentene, cyclobutene and cyclopropene. The exocyclic double bonds exhibit an increase in frequency with decrease in ring size. The exocyclic double bond on 6-membered ring absorbs at 1651 centimeter inverse and is shifted to 1780 centimeter inverse in case of exocyclic double bond on cyclopropane. The allenes show the highest double bond absorptions at 1940 centimeter inverse. Now these can be easily seen in this figure. The 6-membered rings with carbonyl group, example cyclohexanone, absorb at normal value, that is 1715 centimeter inverse. Now decrease in ring size increases the carbonyl stretching frequency. Smaller rings require the use of more p character to make CC bonds for the requisite small angles. Now we come down to alkynes, that is triply bonded. Alkynes contain the C triple bond C group and 3 characteristic bands can be present in them, that is triple bond C H stretching, triple bond C H bending and C triple bond C stretching. As the force constant for a triple bond is greater than that of a double bond, consequently, whereas a CC stretching vibrations occur at 1300 to 800 centimeter inverse and the C double bond C stretching vibration occur in the region of 1700 to 1500 centimeter inverse. The C triple bond C vibrations are observed at significantly higher frequencies in the region of 2300 to 2050 centimeter inverse. The terminal alkynes show CC triple bond stretching vibration at 2140 to 2050 centimeter inverse, whereas the symmetrical or unsymmetrical internal alkynes show either no band or a very weak C triple bond C bond absorption at 2260 to 2190 centimeter inverse. Now the terminal alkynes show a sharp and strong band which belongs to the CH stretching vibration in the region of 3310 centimeter inverse to 3200 centimeter inverse. The sharpness of this band prevents the confusion with other absorptions in this region, that is the NH and OH etc. The CH bending vibrations in alkynes occur as a strong broad band in the region 700 to 600 centimeter inverse. The first overtone of this band appears as a weak broad band near 1375 to 1225 centimeter inverse. Therefore, the frequency of the absorption of CH bond is a function of the type of hybridization of the carbon to which the hydrogen atom is attached. While moving from sp3 to sp2 and to then sp hybridized carbons, the S character increases and so is the bond strength. Coming to aromatic hydrocarbons, the CH stretching bands of aromatic compounds appears as multiple weak bands in the region of 3100 to 3000 centimeter inverse range. Now, it is important, students, to note here that the aromatic CH stretching bands occur at a slightly higher frequency as a shoulder on the stronger alkane CH stretching bands. Then is the CH stretch in alkanes, which appears below 3000 centimeter inverse. Now, besides the CH stretch above 3000 centimeter inverse, two other regions of the infrared spectrum of aromatic compounds distinguish aromatics clearly from the organic compounds that do not have an aromatic ring. In the region of 2000 to 1700 centimeter inverse, a series of weak combination and overtone bands appear. However, they are very weak and are observed only in the case of concentrated solutions of highly symmetrical benzene derivatives. Now, the other most prominent bands are in the region of 900 to 650 centimeter inverse due to the out of plane bending of ring CH bonds. Now, the CH in plane bending vibrational bands appear in the region of 1275 to 1000 centimeter inverse. The bands of the out of plane bending vibrations of aromatic compounds are strong and characteristic of the number of hydrogens in the ring, and hence students can be used to give the substitution pattern. Now, mono-substituted benzene derivatives exhibit strong absorption bands in the regions 690 to 710 centimeter inverse and 730 to 770 centimeter inverse. The absence of any band at 690 centimeter inverse indicates the absence of mono-substituted phenyl rings in the sample. 1,2 di-substituted benzenes give one strong absorption bands in the region 735 to 770 centimeter inverse, but no band in the region 690 to 710 centimeter inverse. 1,3 di-substituted benzene rings give two absorption bands in the region 680 to 725 centimeter inverse and 750 to 810 centimeter inverse. Next, 1,4 di-substituted rings have only one strong absorption band in the region of 800 to 850 centimeter inverse. Now, the first figure is that of toluene, and you can see all the stretching frequencies I mentioned are marked in this figure. Second IR spectrum belongs to 1,2-diethyl benzene, and you can see all those substitution effects in this and the values of the stretching frequencies. The third is the IR spectrum of 1,3-diethyl benzene, and the fourth one belongs to the IR spectrum of 1,4-diethyl benzene, and clearly all these stretching frequencies can be visualized in this. The bands related to other substitution patterns are summarized in the figure. As you can see, the mono, tri and tetra substitutions are clearly marked in this IR spectrum with lines, and these are the out of plane bending vibrations of ring CH bonds in various substituted aromatic compounds. Now, aromatic hydrocarbons show absorption in the region 1650 to 1400 centimeter inverse due to C double bond C stretching vibrations in the aromatic ring. There are normally 4 bands in this region at about 1600, 1585, 1500 and 1450 centimeter inverse and are due to C double bond C in plane vibrations. The absence of these bands indicates the compound is not aromatic. Now students, after having studied all the hydrocarbons in their various hybridizations and aromatics, let us now summarize this module. The stretching frequency of a bond depends on the strength of the bond and the masses of the bonded atoms. Hooks derived an equation to calculate the approximate vibration frequency of a bond. The vibrational frequency of a bond increases as the number of bonds increases between the two atoms. A CC triple bond absorbs at higher frequency than a CC double bond followed by a CC single bond. Hydrogen bonding changes the position and shape of an infrared absorption band. Now stronger is the hydrogen bonding, larger are the effects seen. Next we saw that and we learned that ring size and electronic effects such as inductive resonance effects also affects the vibrational frequency in a particular compound. We also learned cis alkenes absorb at higher frequencies than trans and they are more intense than trans alkenes. The terminal alkynes show stronger CC triple bond stretching bands while internal alkynes show either no band or very weak bands due to CC triple bonds. Now last, the out of plane bending vibration for benzene gives important information about the substitution pattern on the benzene ring. Now students, after having finished this module, we have definitely learned and have gained a better insight into the aliphatics, that is aliphatic hydrocarbons, as well as the aromatic hydrocarbons and the substitution pattern on various types of benzene rings.